Okay, so the third kind of architecture I want to show you is a so-called sequence-to-sequence model or encoder-decoder model. So far, we built a network that can generate new text by predicting the next word in a sequence. But now we want to use a network for some more sophisticated tasks, for example, for translating from one language to another, like you can do online with a translator like Google Translate. So for example, from English to French or English to German. Another task is question generation. So you give in a paragraph of text and you want to generate questions that could be asked about the text together with the answers. So basically generating a multiple choice test, or alternatively, you could also use it to answer questions given an input text. And also text summarization. So given a longer text, you want to condense it into a shorter one. So for this kind of problem, the LSTM network isn't going to be good enough. Yeah, it's not, we can't just predict, let's say, the next German word randomly. We have to make an accurate translation based on the English input text. And for this kind of problem, we're going to use an encoder-decoder network architecture. So the way it works is that basically we take two LSTMs and we connect them. We set up one as an encoder type network and the second as a decoder type network. So the input works just like before with an LSTM. We are feeding in our input one word at a time. In this case here, we have an English sentence that we want to translate. The girl will play football. Now, the new thing is that we sort of encode this into an internal representation. This is typically called a thought vector. And then this input goes into a decoder architecture. And then we decode it step by step. And in this case, generate German output. Das Mädchen wird Fußball spielen. So this is an accurate translation of the input text here. So at each step in the decoder layer, we are starting with this vector we obtained here. In the encoder layer, the thought vector, we apply it, and we do the standard dense softmax output, obtain the first word, goes into the next cell together with the output from the first layer, and this way decode it step by step, in this case, into a different language. So we can use this type of architecture for machine translation. And as I mentioned, we can also use it for a question and answer generation system. So here we have an input text. The winning goal was scored by 23-year-old striker Joe Blocks during the match between Arsenal and Barcelona, and so on and so on. And now given this text, we can have two networks, an answer generation network and a question generation network, where they will generate matching question and answer pairs. So for example, Joe Blocks as the answer to who scored the winning goal, and who won the match would be Arsenal, and who were Arsenal playing? Barcelona, and so on. So it's the same kind of architecture, encoder, decoder, but we use it to generate the question and the answer pairs. In this kind of setup, the first encoder will generate the answers, and then we feed this into the second part, into the decoder, and this will generate us the corresponding question for the answer. If you want to try this out, again, you can do this in Keras, as shown here. For encoding the words in input, we're going to use word embeddings. So the ones we're using here are the ones that come from twelfth. That's, you'll see the link to the repository in the corresponding book chapter. Basically, it's another set of pre-trained word embeddings like the ones we've used before. So for the complete network setup, again, I'll show you the reference in the end. Here, just showing you an example output once you run this network. So on the right-hand side, you see the result from the encoder part of the architecture, which predicts for each word in the input how likely it is to be part of a question. So you can see that was has a rather low probability in terms of softmax to be part of a question, whereas this 23-year-old striker, Joe, has a very high probability to be part of a question. And then the decoder network will generate for a chosen answer range. So here we pick 6 to 9. We can set this to a certain threshold. Will predict a question like who scored the corresponding entity. In this case, UNK stands for unknown. Basically, the network predicts that the word that should go here is not part of the vocabulary that it was trained on. In this example here at the bottom, you can see a sequence where it didn't have a prediction for an out of vocabulary word. So it predicted the question, how much money did he lose? And the answer, 50 million pounds. Okay, so much for a quick overview on 3 types of network architectures and how you can use them to solve various tasks in natural language processing. In the last part, I'm going to talk about some state-of-the-art models which fall into the category of transformers. See you then.